welcome back. So what we're looking at today is 4.4, are you rational? So let's go ahead and jump right in. So for this first part, it wants us to find the roots and the domain for each function. So the roots are the zeros. So remember, when we have it factored like this, it's just going to be what makes each part 0. So our roots would be -5, 2, and 7. Now our domain is going to be all real numbers. All numbers. Now, when it's not all real numbers is when we have the fractional functions. So such as here in this case. So we'd have roots would be none, roots none, but the domain is all real numbers except -5, 2, and 7. So make a conjecture that pairs the domain of a polynomial with the domain of the reciprocal of the polynomial. Note that the reciprocal of a polynomial is a rational function. The domain, I'm just going to put D, of the reciprocal function will not include the roots of the original function. Do the roots of the polynomial tell you anything about the graph of the reciprocal of the polynomial? So the roots are not included in the domain of the reciprocal functions. They cause the denominator to equal 0. So roots not included in domain of reciprocal function. All right, find the y-intercept for 1 and 2. What is the y-intercept for 3 and 4? So for number 1, look back up here, our y-intercept, if we multiply 2 and 7 and 5 together, that'll get us our y-intercept, which gives us 70. So 0, 70 would be our y-intercept for that one. For number 2, it's already in standard form, so our y-intercept is the 6. So 0, 6. Now for 3 and 4, it's the reciprocal of that. So for 3, it'd be 0 and 1/70th. And for number 4, it'd be 0 and 1/6. All right, determine if each of the following is a proper or improper rational function. So improper means that the numerator is more than the denominator. So in this case, the numerator is more than the denominator of 1, so this is improper. Improper is your key word for this lesson. Basically, it means that the degree is higher. So we're looking for when the degree is higher. So in this case, we've got a degree of 3 in the numerator, only 2 in the denominator, so it's improper. Now this one, we have a degree of 2 in the numerator, but a degree of 5 in the denominator, which makes it proper. So that's what you're looking at, deciding just whether or not it's proper or improper. All right, which of the functions above have the following end behavior? As x approaches infinity, f of x approaches 0, and as x approaches negative infinity, f of x approaches 0. So this would be numbers 10 and 12. For the next section, determine if each rational expression is proper or improper. If improper, use long division to rewrite the rational expression such that a of x divided by b of x equals q of x plus a fraction where q of x represents the quotient and r of x represents the remainder. So this one here is improper. We use our long divisions, x minus 1. We have 2x to the third minus 7x squared plus 6. we'd have a 2x squared. I know it's hard to see. So this would be 2x to the third minus 2x squared. Those will cancel. We're left with 6. We take and subtract the 2x cubed minus 2x. We end up with a negative 5x squared plus 6x. So what do we have to multiply x by to get to negative 5x squared? Well, that would be a minus 5x. So we have negative 5x squared plus 5x. So then this cancels. Now we have 5x plus 6. Sorry, negative 5x plus 6. So now what do we multiply x by to get to negative 5x? Well, that would be a negative 5. So we have negative 5x plus 5, which will leave us with 1 left over. So this ends up being 2x squared minus 5x minus 5 plus 1 over x minus 1. So this is what happens when it's improper. When it's proper, such as this one here, we just write proper. Now, I will tell you 17 and 18 are both improper, so you'll be dividing on each of those, okay? All right. And the last section, so finding the domain of rational functions that can be reduced. State the domain of the following rational functions. So for 19, we have y equals x minus 2 over x minus 2 times x minus 5. So domain is all reals except x cannot equal 2 or negative 5. Remember, it's just the opposite of what we have for each of these, okay? Now, each of the previous functions has only one vertical asymptote. Write the equation of the vertical asymptote for 19, 20, and 21. Now, notice, in the numerator we have x minus 2. In the denominator we have x minus 2. Those cancel out. So the only vertical asymptote we have is from the x minus 5 part. So it's only x equals negative 5. So look for what will cancel. What's left over will give you your vertical asymptote. And notice in this last one, 2 things cancel. So be very careful. All right, the graphs of 19, 20, and 21 are below. For each graph, sketch the vertical asymptote. Put an open circle on the graph anywhere it is undefined. So our vertical asymptote for 19 will be right along this line. Our open circle, so where it will not exist, is over at positive 2 over here. So we need a nice little, gonna attempt open circle, kind of, sort of. So be careful with those, but you're just looking for the one that cancels out. So the asymptote, or the part of your reals and roots that will cancel, that's where you're going to put the open circle, okay? All right. If you guys have any questions, feel free to ask. Have a wonderful day.